Okay. Good afternoon. Good afternoon. Um, uh, Good afternoon. Good afternoon. Good afternoon, Gabrielle. Thank you. Uh, okay. Okay. Here we go. Thank you, Gabriella. Good afternoon, Roger. Thank you. Good afternoon, Ariana. Thank you, Ariana. Good afternoon, Genesis. Thank you, Genesis. Good afternoon, Sonam. Thank you, Sonam. Uh, okay. We're going to thank you, Skylar, for the avatar. Um, And thank you for those of you who often show video. I know it's getting tougher and tougher at this part of year for me too. But I am still aware of many of you who have many times shown video. Okay, good afternoon, Brandon. Thank you. Okay, we're going to keep going um, with where we were yesterday. We're going to keep going. Oh, well, in a minute. Oh, I thought Sonam was already. Good afternoon, Yaneli. You. Good afternoon, Sydney. Thank you. Okay. So here we go. I'm just going to pick up where we were Monday. We're in the context, and feel free again, as always. Like we're getting it. The concept we're doing right now is very important for Physics 204, but it's also very important for math in general. Um, well, I'm just going to keep going with where we were yesterday, but feel free to participate and stop me if I land at a concept that you've never understood, that it's always troubled you, or you know you've always had trouble with, or feel free to tell me to move faster if you feel like you've heard this a million times before. But here we go. Here's so where we left off Monday at the end of the period was, well, okay, I'm going to read this out loud in English, and I'm going to tell you what I mean by this. What this says is work, by definition, is the limit as delta x goes to zero of the sum of the f dotted with delta x's. Like that's a mouthful, right? That is a mouthful. So I want to break it, but that's where we left off Monday. So let me break down what that mouthful is trying to say. Well, first I'll read the English. It says, if the displacement is large enough to allow for variations in the force, and if the force varies as a continuous function of position, then total work is the continuous sum of partial works. Okay, even in English, that's a mouthful. So I want to spend a little time, like, in theory, that's what we said last Monday, but what is it that we're saying? Hold on, I'm just going to change the view on the screen. And again, this is like one of these things, like if you could take notes and write down things that I'm saying now. I don't want to turn the page yet. I don't want to overwhelm you with text. But if anything I'm saying right now, you can write down in your own words and submit it to the note-taking portal for points. Please do. I'm saying, okay. First of all, I'm saying that, okay, sorry. First of all, I'm saying Monday, we spent a lot of time dealing with this thing called the dot product and dealing with the fact that force is a vector and displacement is a vector. And what does it mean when you multiply the two of them together to get a product that isn't a vector? Like that was a big emphasis of Monday. That has to do with the vector character of force and displacement. Now, that was Monday. It's still true, everything we said Monday, but that's not my issue right at the moment, okay? I'm saying so put aside the directional issues for a moment and just realize that that in a small in a case of small displacement, work is force times displacement. Like just think of magnitudes. Like like it, oh my God, sorry, I'm a little bit. I'm saying work is force times displacement. In the simplest case, in the smallest case, if there's not a lot of details to worry about, work is force times displacement. In fact, to make it even simpler, if everything is all lined up and the force is in the same direction as the displacement and the displacement's really small, so the force isn't varying, then really in the simplest case, it goes back to like something you might have heard in seventh grade, work is force times distance. 1 joule of work is 1 Newton of force times 1 meter of displacement of distance in the simplest case. Now, what I'm here to address now that we're at a higher level of physics and study and all that is I have to address all the nuances of what if it isn't the simplest case. But let's start with in the simplest case, work is force times distance. Okay. Now, part of what makes cases not simple is if the force direction and the displacement direction are not lined up with each other. That's what we dealt with Monday. Now set that aside in your brain. What I want to deal with now is the other thing that makes life complicated, which is what if the distance is big enough? What if the distance is big enough that the force has room to change? What if we're dealing with different values of force? Then how do you know which force to use to multiply by distance, right? That's like actually the issue that we were last worrying about on Monday. And the answer is, or the first answer is this bit right here up in the blue box. What we said at the end of Monday is, okay, if you're pushing a box along a floor, so you're pushing with some force F and it's displacing along the floor with some displacement like delta X, right? If you're pushing a box along a floor and the delta X is big enough that you have room for your F values to change, then the first thing we say in our minds is, okay, that's okay. If your force changes from place to place, as long as it changes in like chunks, in quantifiable, distinguishable, divisible chunks, then we're just going to add up all the chunks to get the whole. What am I talking about chunks? What do I mean? I mean, what we're saying is, in the case of a discrete sum, if your force changes in discrete, divisible, countable steps, then we can just do a procedure that is captured by that sigma notation. What the sigma notation is saying is, look, let's imagine that in the that let's imagine that you take this big displacement and you divide it into a bunch of individual meters. Imagine that for each one of those meters, there's a specific new different force value. So imagine like if for the first meter we pushed with 10 newtons of force, and then the second meter we pushed with 20 newtons of force, and then the third meter we pushed with 30 newtons. Like imagine that it was clean and easy like that, right? Then what the sigma notation for math is trying to say, the sigma notation is like a procedure. It says set I, the value of I is like a counter, an index, right? It says start by setting your counter to 1. That means look at the first meter. Look at the first meter, delta x sub I, delta x sub 1. Ask yourself, what is the force that's applying to that first meter? Oh, the force in this case, the first force, the force sub 1, the force that corresponds to the first meter. Let's say in this example, it's 10 newtons, right? So the procedure says you set your counter to 1, you multiply the first force by the first meter. So you multiply 10 newtons by 1 meter, and you take that multiple that result and you put it in your bag in your mind. You put it in a bag in your mind. And then you raise the index to 2. Like the sigma notation is being you start your index at a certain value and then you just keep clicking it up and clicking it up every time you do the procedure that's within the sigma, right? So first we multiply the first force, 10 newtons, by the first meter, 1 meter. We get 10. We 10 joules, and we put that in our bag. Then we click the counter, the index to 2. So we go to the next meter. Okay, we look at what the force is for the next meter. Oh, it's 20 newtons. So we do 20 newtons times 1 meter. We get 20 joules. We put that in our bag. Then we go to the next, and the next, and the next, and the next. And we keep doing these products, and we keep throwing them in our bag until I gets to the value of n. What is n? The last value of I. It just stands for the last meter that exists in this path, right? So at the end of the day, that bit in parentheses, sigma is used for a discrete sum, a sum like this, where we can divide the whole into parts that each have their own separate value for force. We add up all the parts by doing this procedure, and the sum of all of these products will be the total amount of work, right? Again, technically, this is just a summary of what I said last Monday or 2 days ago, but I'm saying right now, what we do in our minds when the displacement is large enough to account for different forces, we say no problem. We just divide the displacement into chunks that are small enough for each one to have its own value of force. And we just go part by part. We add up all the parts and we have the whole. Okay? So work would just be the sum of all of the force displacement products. We could be done, and that would be our definition of work. Except then we realize, and this is where we ended up on Monday, we realize, wait a second, that's a good start. That's good logic, but that's not really good enough because in the real world of real space and time, that's not generally how things go. And good afternoon. I'm sorry to people who just, okay, good afternoon. That's not generally how things go in the real world. Like you could divide down, you could take you're moving a box across the floor by pushing it, right? You could take the whole 50-meter displacement and divide it into 50 1-meter chunks, but then you look closely and you're like, wait a second, even within this each 1 meter, the force is changing. It's not like a cartoon, probably. It's not like at the end of each meter, I stop and I go, now I'm going to ratchet up my force to 20 newtons. Oh, now I'm going to stop and ratchet up to 30 newtons. Oh, now like in other words, if you're thinking graphs, nature doesn't usually work like step functions, right? What really probably happens is I'm just smoothly, continuously increasing or decreasing my force as I push this box. In other words, no matter how small I make the intervals, whether they're meters or centimeters or millimeters or angstroms, I keep going down and down and down. No matter how small I make them, I notice the force value changing because the value is changing all the space all the time. It's changing as a continuous function of position. What does continuous, you hear the word continuous in math all the time, continuous function, continuous. What does it really mean? It means infinitely divisible. Continuous means no matter how far down you subdivide it, you still see change, right? So where we ended up at the end of Mondays, we said, okay, if we really want to be realistic about this, the total amount of work for a big space interval, big enough to allow for continuous variation in the force, what we would have to do is take this sum, do this procedure that I just explained, that sigma uh, denotes. We'll have to do this summing up procedure, but We'd have to do it in the limit as delta x approaches zero, right? Like make our little space intervals that we're walking and examining, make them so small that they're as close as possible to to zero, that they're infinitely small, right? Now, I'm not saying I know how to do that yet. I'm not saying that I know how to picture the answer, but I'm just saying, and stay with me, I'm saying if I could do that, that's what I want to do. In order to calculate the work done by a force in some general situation where the displacement is large enough to allow for a continuous variation of force, what I'd have to do is sum up all of the force displacement products in the limit as displacement approaches a size of zero. That's what I'm saying so far. Can I go on? Wait, is that, I mean, that's a lot, but does that make, that's technically a summary of what I said at the end of Monday. But can, okay, thank you. Good enough. Good enough. Okay. So I'm going to go and just notice what, so that's what this like page is trying to say. And just notice the part in parentheses, the blue, thank you. I do appreciate that. And you should submit for points. The blue box, just the sigma part, sigma is what we use when we have a discrete sum. By discrete, I mean a sum of countable, distinguishable, separatable parts. Okay. Now, when we go to the limit, when we take sigma to the limit, well, first of all, when we, you know, from earlier in the class, when delta x is taken to the limit of zero, what we call it dx. Remember from earlier in this class, delta x means small but finite difference between two values of x. When the difference is so small that it's infinitely small, that we're going to the limit as we get as close as possible to zero without actually being zero, we no longer use delta x, we use dx, right? Dx means delta x in the limit as it approaches zero. Well, similarly, when we swap out the delta x for a dx, we swap out, this is a notational thing I'm saying here. We swap out the jagged discrete sigma that we were using to mean sum in a jagged, choppy, discrete situation. When we're moving from that to the sum over a smooth, continuous situation, we no longer use sigma to mean sum. We use a big, long, smooth S for sum. And that big, long S is, as you know from math class, called the integral. What I'm trying to say here, what I'm trying to say. Now, please don't like this is the moment. I'm trying to deal with integrals now. Now, I know you've all seen integrals before. If you're like me, or the way I was at this stage, you may well hate integrals. You may have even gotten an A in calculus class, and you may know how to do a bunch of integrals, but you might not like doing it. And secretly, somewhere in your mind, you might even think or know that you did a bunch of integrals, but you never really liked what you were doing, or sort of knew what it was you were doing, or why, or what it meant. Then, and if then this is your time to pay attention. It is not too late. We need this in a big way for physics 204. But I'm speaking to I'm speaking to all of you right now. Those of you who think you do understand integrals, I'm trying to make a big connection between what you already understand about integrals to what we're doing in physics now. But those of you, and you know who you are, those of you who never liked integrals or never felt totally comfortable with them, don't now say, oh, Jesus, now he's getting into integrals. So it's like too late for me. So forget it. No, 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 no. I'm saying Here is what an integral is. What an integral is and why the notation actually makes sense is an integral is a continuous sum of products. If you understood what I was saying Monday about, I look at the first, like, in fact, yes, I'm saying, I'll go back to that page in a minute if you want. Oh, wait, no problem. Thank you. Good afternoon, direct chat. Nope, thank you. Okay, I'm going to be mathy here for a second. And I'm saying this again. Don't think that now that I'm doing integrals, it's time to fade out or give up. It's a second chance. It's a third chance. It's a fourth chance. I know in my heart you could be doing integrals for semesters and never like them or never really understand what you're doing. This is your opportunity to maybe take a fresh look. Okay. And again, we do need this for Physics 204. So what I'm saying, I'm going to be mathy for a minute. I'm saying, what is the integral from x1 to x2 of f of x dx? What does that mean? Like, what the heck is that? Well, assume that y is a function of x. Assume x is some independent variable, some input, and y is the output, right? Like any math function you have at all, right? When we do the integral of f of x dx, what we're doing is we're walking along the x-axis of like whatever it means. We're walking along the x-axis. We're taking steps along the x-axis, and at each step we take, at each little delta x we take, we're asking what is the value of f of x? Like what's y? What's the dependent variable there? So if we were in a graph, we're taking a step along the x-axis and then we're looking up and asking what's the value of y right here where I'm standing? We multiply the two together. Like we multiply the value of the x step, say it's like 1 meter, by the value of the y of y, say it's 10 newtons. We multiply the two together. We put it in our bag, and then we take the next step, the next 1 meter step. We look up, say, what's the value of y? Oh, it's 20 newtons now. We multiply 20 newtons by 1 meter and get 20 joules. We put it in our bag, and we take the next step. The only catch is we're doing this in the limit where each one of our steps is infinitesimally small so that we can catch every single possible value of f. I'm not saying I know how it's possible to do this. I'm just saying, yet. I'm just saying this is what we're doing. When we do an integral, we are doing a continuous sum of products. That is, we're doing a sum of products in the limit where the second value of each product is infinitely small. What are the products? The products are the value of the independent variable step that we just took times the value of the dependent variable. Always, this is what an integral is. That's why in math class you think of an integral as the area under the curve or whatever. And when you originally break it down, you think of it as a bunch of rectangles under the curve. And it's all like very like, whoa, what's going on? Each one of those rectangles is just you taking a step along the x-axis, and that's the width of the rectangle, and asking what's the height of the rectangle, what's the value of the function at this point, right? And then taking the width times the height, putting it in your bag, and taking the next step. We're just doing, so that would be a sum. If you take that sum to the limit, it's a continuous sum. I'm trying to emphasize, like it looks like a lot of notation, but if you understood what I was saying Monday, or anything I'm saying about physics, about walking, multiplying, walking, multiplying, walking, multiplying, putting all those multiplication products into your bag, and then at the end, opening up your bag and looking what the sum of all of those products is, that is what an integral is, as long as when you did that, you were in the continuous case, in the limiting case, not the jagged countable case. So again, I'm going to say, we use sigma to mean sum, and I think most of you do understand sigma. It means step, step, add, step, add, right? Well, the integral symbol is just a sigma, only smoothed out. They both mean S for sum. An integral is a sum, a continuous sum of products. What's the product? The value of the dependent variable times the step of the independent variable. And again, please, I will move on in a second. I know. I mean, I will. But notice when we went from discrete to continuous, when we went into the limit as delta x approaches zero, the delta x turned into a dx because it got infinitely small, and the sigma turned into an integral sign because it got smooth. An integral is just a smooth sum of products, a continuous sum of products. In general, in math of any function at all. And that's why there's always a dx or a dy or a d something in the integral thing. It's not just there to annoy you or confuse you or make you memorize something. It's there because that's what the integral really means. It is the smooth, continuous sum of products. The product of the dependent variable times the independent variable, always. Okay? Now that's in general what an integral is. Notice, and I'm gonna go back to physics, okay? But please notice, and I'm screaming because I just got to admit to you, I know that calculus is like required to do physics. That's like the tradition or the protocol we follow in life these days. But I know from personal experience that it might be just as useful for many of you to require physics for calculus. Like it has nothing to do with the teachers or anything like that. But like I did, please just know again, I chose to be a physics major undergrad and graduate school. And I was taking a bunch of calculus and doing a bunch of integrals before I ever felt comfortable with what they were. Finally, at some point in doing physics, retrospectively, the calculus started making sense to me. Sometimes for some of us, we need to see it in the physics in order to see whatever. Everybody's different. But don't give up on the calculus that you are going to need for next semester. We do use it much more heavily in 204. It's never too late to get it by seeing it in a physics context. So notice this. So far, I have not said one thing about the fundamental theorem of calculus. Like I will, but I haven't. Notice I have not said one thing about antiderivative or anything like that. What I'm trying to emphasize right now is what the integral actually is. I'm not talking about how to get it. I'm not talking about how to compute it. In fact, nothing I've said even means that we don't even know necessarily that we could get it yet. I mean, we can, but we don't know that based on what I'm saying. I'm saying, what is the integral? It is the continuous sum of products. That is what the integral is. It is a continuous sum of products. It has not, right at this, that's what it is. That's what it is. How to solve for it is another thing, but that's what it is. So let me go back to physics now. Well, okay, no, I'll go back to. Let's see. Okay, no, I explained all this. Okay. Now in physics, so physics work is an integral. What is it the integral of? It's the integral of force times displacement. So here now in physics, our independent variable is x, is space, and our dependent variable is force. So now, when I say picture yourself walking along the x-axis, and every step that you take along the x-axis, ask what the value of the dependent variable is. The dependent variable now in physics is force, right? But now it goes back to this other subtlety from last Monday. Every time we take a step now along the actual x-axis of actual space, like every time we actually take a meter step forward in space, we're asking, what is the force vector acting on us during that step? And we're taking into account the fact that force vector is a vector and has direction, and that direction bears some angular relationship to the direction that we're walking, right? In physics, we're not just multiplying a number by another number, we're actually multiplying a vector through space by another vector called a force vector. We're using a dot product. Okay, so that is a specific kind of integral. When the integral that you're doing is an integral of a dot product. Here, okay, I'll just read this English out and then I'll say what I'm saying. This is a new definition. This is a specific kind of integral now. Like what I was just explaining was integrals in general. And again, an integral is a continuous sum of products. It's a sum of products taken to the limit. That's what an integral is. Now, a path integral is a specific kind of integral that is used in physics all the time. A path integral is what happens when the dependent variable is a vector and the independent variable is a vector and the two vectors are being dot producted together. And more specifically, when the independent variable is specifically displacement. So I'll read it in English. It says a path integral is an integral of a dot product of some dependent variable vector with an independent variable of displacement. That's what a dot product is. So whenever the independent variable is literally displacement vector, like dx with an arrow over it, and you're dotting that with some dependent variable vector, then we call that a path integral. Why? Like what? Because we're saying integration in general means walking along the x-axis, whatever the x-axis represents, and asking what's the value of the dependent variable as you walk along the x-axis. Like that's what an integral in general is. But again, that's like math. Like the x-axis could mean anything. It could mean meters of displacement, or it could mean degrees of temperature, or whatever, right? And you can integrate anything with respect to anything if you have a function. But now, if we're actually in space, if we're in like physics, if the x-axis that we're walking along is literally an x-axis of space, so every step we take is a certain distance measured in meters in a certain direction of space. If our independent variable is actually displacement, then what we're walking along when we picture ourselves integrating, we're actually walking along an actual path of space. And every step we take, we're asking, how does the dependent variable line up with our path? So in the case of physics work, right? We're picturing ourselves like we're pushing a box along a horizontal floor and we're pushing it at some angle. So we're looking at every step, every infinitesimal step along the floor, every infinitesimal like bit of sliding that the box does along the floor. And we're asking at that infinitesimal bit of horizontal displacement, how much does the force affect this box's path or motion along the path, right? We're dot producting the force vector with the displacement vector. We're right? We're doing that thing that we said Monday, where we take the magnitude of the force vector, multiply it by the magnitude of the displacement vector, and then multiply by the cosine of the angle between them to see how parallel they are, right? Whenever you do that, when you do a dot product between a dependent variable vector and an independent variable vector of space, whenever you do that specific type of integral, we call that a path integral. I'm going to write it again. Okay. So in general, an integral is a continuous sum. Work is a path integral. It is specifically the path integral of force. It is how much the force is acting throughout some path of displacement. Um, um, okay, and for I'm going to pause. Actually, I mean, we're actually okay on time. So, are there any questions or comments or anything about that? Like, does that make any sense? Okay. If all right. So I'm going to leave that content there for a moment. Thank you. Thank you, Direct Chat. That's actually really helpful. Okay, cool. All right, thank you. That's good enough for me. Those of you who just went in the Direct Chat, but please submit for points. You deserve them. Thank you. All right, so um, this is what we're going to do now. As promised or as is needed, I'm going to switch. Hold on. I'm going to turn off the recording. Hold on a second. And we're still having class. Don't go anywhere, but I am turning off the recording. Ooh,